Welcome back, ecologists. We're going to continue our discussion of populations and ecology and cover those slides that we did not finish in lecture. So I'm going to take us all the way to slide number 22. We're now going to get into the topic of scale and energy allocation. So we're going to discuss ways that populations maximize reproductive success, which means we need to understand some of the variables that go into population growth. So one of those variables is generation time, and it's rather intuitive that smaller organisms have shorter generation times. That is, it takes less time for small animals, and in this case protists, to mature to the point where they themselves can reproduce. And conversely, large animals tend to have longer generation times, including all the way up here sequoia trees, which have generation times of hundreds of years. And that is primarily because of the size of the organism. It takes just that long for the organism to grow to its mature size. So this brings us to the topic of demographics. And demographics is really the study of age structure. And these are some variables that are important in demography. And that is to say, we're looking at the number of individuals within the population that fall within different age categories. So, in order to know this, you have to track the population over time. So one of the things that we track is cohort. What does a cohort mean? Cohorts are groups of individuals of the same age or the same class. Then there's fecundity. And fecundity is a measure of the number of offspring produced in any given time. Another measure here is mortality. That would be the opposite of fecundity. And mortality is the death rate in any standard time. So fecundity, how many are being produced. Mortality, how many are dying. And all of these factors here strongly influence population growth rates. So let me give you an example of how we might measure this. What you're looking at here is something called a life table. And this particular life table happens to be for a particular kind of grass, but life tables can be made for animals just as well as they can for plants. And what you're seeing here is we start out with a population of a particular size, and that's what this number is here, 843 at time 0. So you go out, you count how many are there, and they're all of about the same size, 843 of them. And then you track it. You come back at some other point in the future, let's say 3 months later. Time 1 is 3 months later, time 2 is 6 months later, time 3 is 9 months later, etc. And each time you come back, you count the number of surviving individuals. Remember, you started out up here with 843, so at time interval 1, there's only 722 remaining. At time interval 2, there's 527 remaining, etc. And so you can use this information basically at time 2, for example, 527 out of 843 is 62.5% surviving. And that means you can estimate how many die, so you know your mortality rate as well. But another thing is you can measure fecundity during this time. So not just survivorship, you can measure fecundity. Here's how many seeds are produced during that period of time. So life tables are really valuable. The part of this that we're going to focus on right now is just this right over here. We're only concerned with, as time goes on, how many of these organisms actually survive. So this is population demography in a nutshell. All right, let's draw what's called a survivorship curve. And we do that. What is survivorship? Survivorship is really the percentage of the population that actually makes it from one period of time to the next. And we can take that life table data and we can express it on an XY plot so that it looks something like this. And you see 3 different graphs here, and these depict the 3 most common varieties of survivorship. And we've given them names here, and I'm going to show you a couple different varieties of this. Organisms that tend to produce huge amounts of offspring, but most of them pretty much die within the first period of time, we call those type 3. And oysters would be a good example of that, where they have a whole bunch of reproductive output, but the number that actually survive and then continue on is very low. But once you get to that initial die-off, survivorship tends to be pretty good. Then there's the organisms who have a more or less uniform survivorship. That is, it doesn't matter what age they are, their chances of living or dying tend to be the same across all ages. So the hydra, the little hydroid, freshwater hydroid, hydra, is an example of type 2. Type 1, a perfect example would be humans, where survivorship is actually really good among the young. And then eventually you hit old age, and you can get to be so old that the survivorship drops off rather rapidly. So we are a good representation of type 1. So, for example, that grass that I just showed you from the life table, if you were to plot that grass, it would look like this. So on an exam, for example, if I was to show you a graph like this, could you tell me what type of graph it is? What type of survivorship curve it is? The answer is it's type 1. So this is an example of how we might view survivorship curves on the exam. Okay, so type 1, type 2, type 3, these are just some characterizations about them. Type 1 mortality is mostly among older individuals. Humans we brought up, but another one would be like sheep. That's the reason why we put Dall's sheep here is because Dall's sheep were the was among the first studies to demonstrate the difference between type 1, 2, and 3. So Dall's sheep, perfect example of type 1. Type 2, American robins. That is to say, it doesn't matter how old an American robin is, the survivorship at all ages tends to be the same. And then type 3, that's where you have huge mortality in the young, followed by high survivorship. And sea turtles are a great example where only about 1% of all those sea turtles all those eggs that are laid actually becomes a sea turtle that is able to reproduce on its own. Okay, so let's get into the nitty-gritty of life history. We've already discussed kind of the connection here between natural history and natural selection. And remember, natural selection favors those traits that actually maximizes reproductive output, or I should say, not just reproductive output, but survivorship of your offspring. So you could produce 1 trillion babies, but if none of them survive, well, that's not a good survivorship. You need to have some that make it to reproductive age themselves. So we need to know how long an individual lives, and we also need to know how many young does it produce in its lifetime. And obviously, you want to maximize everything, right? You want to live a really long time. You want to reproduce a lot and put out a whole bunch of babies all at one time. And you want to also do this as often as possible, like have babies every single second of every single day. Wouldn't that be nice? I mean, wouldn't that be the optimal to go ahead and maximize all of this? But you can't do that. It's not feasible. And so my question to you is why? And hopefully it will occur to you that you only have a finite amount of resources that you can put towards any one of these. So if you want to maximize survival, that is, put all of your energetics into survival, great. But that means that you're going to be shortchanging yourself in the other three measures here in reproductive output and or the quality of reproductive output, and then also in how frequently you can have those babies. So this is all about energy allocation. Again, as a lion, let's say, or a gazelle, or whatever animal you want to think of, You can only eat food and transfer that food into usable material so quickly. You cannot go faster than your own physiology can do it. So if you're a lion and you're eating as many baby gazelles as possible, well, that's great, but you're only going to be able to eat one maybe every few days or so, and you're going to get full. So um, if you put your energy into, let's say, these four basic categories, a quarter of it into maintaining yourself, a quarter of it into actually growing, a quarter into defense, and maybe a quarter, the remaining quarter, into reproduction, well, that's a good strategy, but maybe, just maybe, let's say that it's not necessary to put so much energy into defense because you happen to live in an area where defense is not as is necessary. It's not as useful. Maybe maintaining yourself is a little bit easier because you are living in your food source, for example. So allocating 25% to maintenance is not necessary. And maybe it's all about growth, right? Maybe growth is the thing that is most important. Well, if that were the case, well, then over evolutionary time, the combination that produced the most successful reproductive output may look more like this one over here on the right. Um, you might think, oh, well, I'm going to shortchange myself on defense, maintenance, and growth and just pour everything into reproduction. But perhaps by doing so, shortchanging yourself in those other three ways actually reduces the amount of offspring that actually make it, that actually survive, even though you're putting out a greater number of babies initially. And so this allocation is actually quite well known, and it's been demonstrated a lot of times. This is the just like the textbook classic example, the darter fish. In this case, the relationship is actually quite tight here on the right, where here you have female size on the x-axis and you have numbers of eggs on the y-axis, where the bigger females are putting out more eggs. Okay, that makes perfect sense. That's probably true of all fish, and we suspect that that's true of most invertebrates too. And however, there's an inverse relationship. So there's the opposite relationship, which may not be quite as tight, although it's still statistically testable, or I should say statistically demonstrable. You have egg diameter here on the x-axis and the number of eggs on the y. Clearly, if you are producing a large number of eggs, the diameter of those eggs tends to be small. Whereas if you put out fewer eggs, then you can pour more energy into creating greater diameter eggs, which means the bigger the eggs, the more likely they are to actually survive to the point where they develop into reproducing individuals themselves. So what strategy do you want? Do you want to have high quality eggs, or do you want to have more numerous eggs? You can't necessarily do both. So this is a classic trade-off here. Okay, so let's now get into population growth. Oh yeah, this demonstrates that relationship there. Okay, let's get into population growth. I am going to throw out here a few equations, so don't get scared. The math actually isn't quite that bad, and I'm going to demonstrate to you what each of these variables actually means. There's only two actually in this graph, or I'm sorry, in this equation. So let's take a look. Okay, exponential growth, the rate of growth, the intrinsic per capita rate of growth, is actually measured as this letter here, R. So what is R? What is the growth rate? The growth rate takes into account two sets of phenomena that occur in populations. This B stands for birth, that D stands for death, the I stands for immigration, and the E stands for emigration. So immigration is coming in, emigration are those things that are leaving. So if you want to know whether a population is growing or shrinking, you need to know its birth rate minus its death rate, and you need to know the immigration minus the emigration. If you have more births than deaths, then this is a positive number. If you have more deaths than births, then this is a negative number. And the same thing over here. More immigrations, then then this number is positive. More emigrations, this number is negative. And you add these things together and you get R. And R is that intrinsic rate of growth. So I want you to imagine a population. Pick a number. Let's say that there's 1,000,000 things there. There's 1,000,000 organisms there. And you play this little calculation. You account for all the births, all the deaths, the immigrations, emigrations. And in the end, you end up with 1,000,010. Okay, so your population from point 1 to point 2 increased by 10 individuals.